Okay, next topic is actually the AC analysis. So this is basically covers the AC analysis. AC analysis. So we already discussed about the DC analysis of the transistor. So this DC analysis basically focused on this biasing. So we discussed four different biasing techniques and how we can basically place the Q point or the operating point of the transistor in a given region. So there we discuss about the device characteristic, which is basically extracted from the data sheet. And at the same time, we discuss about the circuit characteristic, which is actually the DC load line. So how do we get the DC load line is like, so we follow a couple of steps. First, so we need to remove the impact of capacitors and inductors, because now we are dealing with DC circuit. So we replace the capacitors with open circuit element and inductor with a short circuit element, and we simplify the circuit to a circuit pair which is equivalent, DC equivalent model. So for this DC equivalent model, we don't have capacitors and inductors. So we just remove or replace these capacitors with open circuit element and inductors with a short circuit element, and simplify the circuit. So which basically identified as a DC equivalent model of this particular transistor circuit configuration. So based on this DC equivalent model, if you apply this Kirchhoff voltage law for the collector emitter junction, and if you modify or rearrange the terms to uh, get this kind of equation, IC, which is equals to kind of a constant times VCE plus a kind of a constant. So if you manage to rearrange the terms which represent a kind of a linear equation of VCE and ICE, this basically gives the load line. So this is the load line of the circuit. So this is the load line. So then we can just draw the load line on top of this device characteristic. So the load line itself shows the circuit characteristic in DC domain. So then we can easily decide whether we can place the transistor's operating point in active region or cutoff or saturation, depending on the requirement. So if it is amplifier, we know that the cutoff, or we know the operating point of the transistor should be placed in the active region. So we can select a suitable operating point along this load line. So once you set the operating point of the transistor, we can basically identify the Q point values, base current, collector emitter voltages. So based on those values, we can easily calculate the required resistors. We need to place it in either a base terminal or collector emitter terminal. So we basically discuss how we can select these different resistors in different arms according to the given current and voltage requirements of the Q point or the operating point. So it's just a kind of a Kirchhoff voltage and current law. So you can apply this KCL and KVL for this transistor circuit. So we know that we can basically take two, or we can get two equations by applying Kirchhoff voltage law for the input circuit and the output circuit. So other than that, we can get these two equations from the fundamental laws. So which is like IE equals IC plus IB, and this IC equals beta times IB. So with these four equations, you can basically find out what are the resistance value we can ideally place on these different arms. So once you plug those values and implement the circuit, so if we are exactly matching with the analytical value, so you will basically place your Q point of the transistor as we plan. So if it is not the case, so if we basically align with the practical values we need, we can get it from the market. So then so the Q point of the transistor would basically vary accordingly along this whatever the DC load line. So we can then and come closer to the real requirement by doing this mathematical calculation or doing this analytical stuff. So then from that point of onward, you can do a kind of a trial and error mechanism based approach to get the exact Q point and the resistors and whatever the required electronic elements. So the next would be like so we can move to the AC analysis. So we discussed that once we make this transistor properly biased, so we can feed a external input to get a kind of amplified version of that one. So then once we are dealing with this AC quantities which we can fed through these external devices like a mic or kind of thing, so the transistor behave in a different model. So now the objective of having this couple of slide set and this discussion is entirely focused on how the transistor behave in this against this AC quantities, how we can model this transistor circuit with this a kind of and model it and get the certain set of parameters which basically describe the transistor configuration and the circuit parameters. So here what I want to highlight is one thing is like, so initially we discuss about this simple notations. So if we have this capital letters with the capital subscript, so these basically refer the DC quantities. Similarly, if it is a kind of a pure AC quantities, so we can use the capital letter with a simple subscript. So if it is simple and simple subscript, these are basically instantaneous values. Like for example, for a given time, so what's the current flow through the base? So it becomes the simple IB. So this is for a given time, what's the base current? So for a given time, this is the collector emitter junction voltage. So this quantity may be sum of these two. So VCE plus VCE. So this instantaneous quantity may be the combination of this DC value and the whatever the AC value we feed through external source. So we identify three quantities based and demarcate or differentiate with different notations. If we have this capital letters with capital subscript, so we are dealing with DC quantities, capital letters with simple subscript, so AC quantities. If both are simple, so then we are basically dealing with instantaneous quantities. So similarly, we can use this physical resistors like RC, RE, RB like that. And if it is a kind of an instantaneous value, so you can think of this kind of a notation, simple RE. So it means the emitter resistance. So it's a kind of a dynamic value. So it's a kind of instantaneous quantity depending on the operating point of the transistor. So if it is a fixed physical resistance, you can just use this kind of a notation. If it is a dynamic one, so then you can use this dynamic resistance. Okay, so then so sticking to that symbolic notation, so we can move to this AC equivalent model. So we can model our transistor. So during this discussion on this transistor BJT configuration, So we basically stick or focus our discussion only for this common emitter configuration. So during this AC analysis as well, we simply focus on this common emitter configuration only. So this is a commonly used configuration. So the analysis is basically focused on this common emitter configuration. So there are basically two models. One is like hybrid phi model. So this is the commonly used model in most of the cases, because this model can basically address this high frequency, low frequency scenarios both with a given model. But in this case, so for the simplicity, we stick into this very simple model called RE model. So then once you go through these steps of analyzing a circuit in AC domain with this RE model, so it's a matter of replacing this transistor model with this hybrid phi model. So the calculation and everything is very similar to this RE model. What I want is like first we can choose a very simple model and see how we can evaluate the circuit to analyze the circuit in AC domain. So then whatever the complex model can be replaced this one and do the calculation or analysis accordingly. So here we basically stick into this RE model. So this is the RE model. So we can replace the transistor like this. So this is your emitter. So this is the emitter, and this is your base. So this is your collector, and these are the currents. So this IB, the base current. So this IC. So then whatever the current simply flow to the ground is like the sum of IB and IC, or the current flow through the emitter is simply the sum of IB and IC. So here we have a kind of a resistor. So beta is the DC gain, and this R is a kind of a dynamic resistance. So dynamic resistance. So we'll see what's this dynamic resistance is. So and so we know that with this beta, this DC current gain, whatever the current flow through the collector would be a kind of a product of beta times the IB. So then similarly we can claim that, so whatever the current fed to the base would be simply multiply with beta and flow through the collector. So then we can introduce a kind of a current source to the collector terminal. So this is a current source. So this is a current source. Again, this is controlled by the base current IB. So this is a kind of a current control current source. So current control current source, we can simply map this input output relationship through this current source we include into the output side. So before more, yes, yeah, okay. So this is the base current and collector current. So we have this input resistance. So place into the input circuit. So this is actually the input circuit. So this is your input circuit. So this is your input circuit, and this is your output circuit. So this input circuit basically has a kind of a dynamic resistance. The value of the dynamic resistance is beta times RE. So we'll see what is this RE actually. So in the output circuit, we have a kind of a current control current source, which basically emphasize the relationship between the base and collector current. So this is the very simple RE model, and you can see the phi model as well. So for the phi model, there are a lot of dependent parameters. So we have this HIE, HRE, HFE, HOE. So we basically have four system parameters, but if it is a RE model, so it's just a one parameter model, RE. So we know the beta, which is the DC gain. So if you know the RE, or if we can manage to calculate this RE, we can simply stick into this RE model. But if it is a phi model, so you have to cater for these four parameters: HIE, HRE, HFE, and HOE. So the calculation or the evaluation or analysis is very similar, and we will first select RE model and see how we can progress on this analyzing a circuit in AC domain. So then it's just a matter of replacing this RE model with phi model. So see, like so it's very similar. So this is your emitter, this is your collector, and this is your base. So you can just remove this RE model from the rest of the circuit and place this phi model there. So then we have this different type of resistors, and we have a voltage sources, current sources in the circuit. So you can just deal with voltage sources, current sources, and resistors, and you can basically do the analysis accordingly. Yes, so then yes, now how do we, so if you are given a kind of a transistor circuit, so we found that if we are dealing with DC quantities, we should basically simplify the circuit to the DC equivalent model. So DC equivalent circuit. So in that case, we simply replace the capacitors and inductors with open circuit and short circuit element respectively. So with that simplification, you can simply convert this the real transistor circuit configuration to the DC equivalent model. So then only you can apply this Kirchhoff voltage or current laws for DC domain. Similarly, if you are dealing with AC quantities, so you can simply get a AC equivalent circuit. So this is the AC equivalent circuit. So in this case, you have to simplify the real transistor configuration to a kind of a AC equivalent circuit. So how do you get the AC equivalent circuit? So this is the transistor configuration which we are focusing on. So this actually has a voltage divider bias mechanism to bias the transistor or place the Q point into a certain well. And in addition, we have this collector resistor and emitter resistor. So we have a bypass capacitors, coupling capacitors, and this external source is basically connect to the transistor circuit through this coupling capacitor. So external source has a voltage of Vs and internal resistance of Rs. So this is the kind of a transistor configuration, or transistor circuit configuration we are now looking into. So we can take the output from these two terminals. So you can, if you want, you can connect a kind of a load resistance here. So then it's perfectly fine. So then we have a load resistance, which is basically coupled through C2, and we have an input having an internal resistance of Rs coupling to the circuit through C1. So we have bypass capacitors, we have voltage divider bias method to bias the transistor. So we have collector and emitter resistors as well. The supply voltage is VCC. So if you basically get the DC equivalent, so you can simply replace these capacitors. So you can simply replace this capacitor with open circuit. So then basically you can simply remove the source, and you can simply remove the loads as well. So then ultimately you will ended up with this kind of a circuit for as this kind of a circuit as a DC equivalent circuit. So this is the way we get the DC equivalent circuit from the whatever the actual circuit configuration. So now we can look into that, how we can get the AC equivalent circuit. So in DC mode, what we do is we simply replace the capacitor with open circuit element and inductor with short circuit element. So for this case, what we can simply do is we can replace the capacitors with short circuit element and inductors with open circuit element. So how you can achieve it? So we know that the current flow through the capacitor is equals to C times the derivative of the voltage across the capacitor. So let's assume that if this voltage is having a high frequency, so you don't need to go to that. So we can simply discuss through the impedance. So we know that for the impedance of the inductor is simply J omega L. So impedance of the capacitor is simply 1 over J omega C. So for this case, if your frequency or the operating frequency of the circuit is very high, so this creates a kind of infinite impedance. So if you are dealing with a kind of infinite frequency, so what about the capacitor? So this basically introduces zero impedance. So that's the root cause for this replacement. So let's assume like we are using kind of time varying quantity, AC quantity with a reasonably high frequency. So then we can simplify the circuit by replacing this capacitor with short circuit element, because for a high frequency signal, so the introduced capacitance or the impedance of the capacitor is zero. So that's why we simply replace it with short circuit element. For the inductor, we know that if it is a kind of a high frequency signal, so the induced impedance of the inductor would be infinite, so we can replace it with a kind of a open circuit element. So then the first we have to replace capacitors and inductors through the short circuit element. Okay, so this is very simple. So you can simply replace this capacitor. So this capacitor gets short. So this is again short. So this is again short. Okay, so what happens to the supply voltage? So now the supply voltage itself is a kind of a DC quantity. So we'll simply remove the impact of this VCC. So how do you remove the impact of VCC? So we set it to 0. Set it to 0. So once you set the supply voltage to 0, so which means so we basically grounded that terminal. So the potential is 0 means, so it's just a kind of a 0 volt. So then once you set this one, it means like, so your VCC simply replace with this kind of a ground arrangement. This is 0 volt. Because VCC is a kind of a DC quantity, so we can ignore the impact of this supply voltage. So how do we ignore the VCC? We just set the value of the supply voltage to 0. Once you set the value of the supply voltage to 0, it definitely becomes a kind of a 0 potential terminal. So then it's like, so this VCC becomes a 0 voltage. Okay, so now I just replace this VCC with this kind of a ground arrangement. Okay, so then we remove the supply voltage or the impact of this external DC source, and we replace all the capacitors with the short circuit element and inductors with open circuit element. Now the circuit looks like this. So this collector is basically grounded now, not the collector. So the supply voltage is simply replaced with the 0 volt. So it's basically grounded, and this so the C2 is short circuited, CE is short circuited. So then you don't see this emitter resistance anymore because this is short. So then there won't be any RE there. Whatever the current is simply grounded through the C3. So that's why we don't have RE there. So we have RC, and this is short circuit, and C1 also gets short circuit, and so then we have this external source and the internal resistor coming to play. So we have R1 and R2 there. So this is the simple circuit. So now what we can do here. So let's think of simplifying it further. So now we have a transistor here. So we have transistor. So this emit is simply grounded. So I'll just draw this one. So this is already grounded. So this is base and collector. So what happens to the collector? So it basically grounded through RC. So then if I draw it, so this collector is simply grounded through RC. So what's the output voltage? Where we basically measure the output. So it's basically between the collector and the ground. So this is your collector and this is your ground. So then this becomes the V out. Okay. So then from base side, so once you come into this node, so we have R2 simply grounded, base R2 ground. So what about this R1? Again base R1 ground. So then we have short circuit path, RS and supply voltage and ground. RS, supply voltage and ground. So this is your VS, this is your RS. So now what happens? So if we carefully look into this, whatever the output we obtained here, so if it is a DC circuit, so this RC is simply connected to the supply. But with this AC equivalent model, RC is simply connected across this VCE, and it simply uh, connected your collector and the ground terminal or emitter or whatever. For this case, it's ground. So RC is simply connected between the collector and the ground. So in the voltage divider bias scenario, so you have this divider arrangement in the DC equivalent circuit. But once it comes to the AC equivalent circuit, so R1 and R2 become parallel. So these kind of simplification would be possible once you convert the real exact transistor circuit configuration to AC equivalent. So how do we proceed with obtaining AC equivalent? First, replace the DC supply with a short circuit so we'll claim like this. So first, set VCC to 0. So the second, replace capacitors with short circuit and inductors with open circuit. So if you do these replacements, so then you can basically simplify the circuit to a different level. So we have this kind of arrangement initially. So this is the exact circuit. So if you do the DC equivalent, we found that this is the effective component for DC analysis. So once it comes to the AC, so now the circuit becomes this. This is AC. So hope you are a bit comfortable of converting this circuit to this AC domain. So let's move further. Okay, so what I want to highlight here is actually, so now we know that we have this different current flow into the node and flow from out from the transistor as well. So then we cannot analyze this without having a proper sign convention. So the sign convention is actually, so we basically adopt into this two-port network. So for the two-port network, so if you think about the transistor in a common emitter mode, so we know that this emitter terminal is common for both input and output circuit. So this is your base, this is your emitter, this is your collector. So then we can map this transistor to a kind of a two-port network. So we have two input port and the output port. So input port would be like base and the emitter. Output would be collector and the emitter. So we can in the common, not even in the common emitter model configuration, for this particular configuration, so we can model the transistor using a two-port device. So this then device itself is a kind of a black box, and we have two terminals come into the black box and two terminals coming out from the black box. So the what are the two terminals which reflects the input scenario, base and emitter. So these collector and emitter terminals are the corresponding outputs, our output port. So then again, like, so we have to stick into the sign convention. So if you are marking the currents by assuming that this system or the transistor is a kind of a two-port network, all the times currents should be flow into the node. But we know that depending on the transistor type, whether it's an NPN or PNP, so the current flows are simply different. But if you just replace it with a kind of a two-port concept, so definitely those currents should be flow into the node. Okay, so this I is the AC current flow into the node. IO is actually the output current flow into the node. But in the actual scenario, the current of the system is flow out from the node. So then you can just consider it as a minus of that value. So the sign convention is all the current should be flow into the node. And the voltage are basically marked like this. So this would be the plus and this would be minus. So this is having higher potential compared to this one. So the voltages are basically like that. We input and we output, and the currents are basically flowing into the node. So this is the simple concept. So then yes, then we can define two another parameters called input impedance Zi and the output impedance Zout. So the difference between this input impedance and the definition of this input and output impedance is like this. So it means like, so you have a kind of a resistor here. So this is your input impedance. So then Zi can be easily evaluated by dividing this Vi with the current flow. So once you divide the Vi input voltage with the current flow into the node, so it basically gives the input impedance. So this is your input impedance. So this is your input impedance. So how do you define the output impedance? It's again very similar to this one. So you may have kind of a resistive or impedance here. So similarly you can take this ratio of V out and I out, but so keep in mind, so this is a kind of a network. I mean, like, so we don't know like what happens inside this system. It's a kind of a black box. So then we should basically ignore the impact of the input. For example, if you see this previous RE model, so there is a current source basically. The value of the current sources depends on the input parameters. So then if you basically evaluate the output impedance without ignoring the effect of input, it gives us something else. So for this case, if you really want to evaluate the output resistance, you need to basically remove the powering source for the input. So we know that the in the AC domain, so the power is basically given by the external AC sources. So which is the actual input to the transistor circuit to amplify. So that input should be 0. Otherwise, so this particular black box model have internal dependencies between input out and output. So if you just evaluate the output impedance without making your input 0, so there may be some additional impact. So additional correlation induced due to this input values, input sources. So once you evaluate the output impedance, keep in mind, so you have to set the input to 0. So then only it gives a kind of a exact output impedance. So your input impedance is just a ratio between voltage and out current. But if you evaluate the output impedance, keep in mind again the output impedance also equals to V out over I out, voltage and the current ratio, but your input should be 0. So then you can basically evaluate the voltage and current gain. So you have a output voltage of V out and the input voltage of Vi. So then you can basically claim that the voltage gain would be V out over Vi. Similarly, you can get the current gain AI current gain. So it's just a ratio of output divided by input. So in that case, you can simply evaluate the voltage and current gains. So let's think about the voltage gain. If you basically voltage gain or current gain once you connect a load. So now we basically connect a resistor to the output side. So we basically stick into the sign convention. So we have V in, current flow into the node, and current again flow into the node from the output side, and we have RL. So what happens if we connect a load to this two-port network? So what about the voltage drop across the resistor? So it should be like this way, isn't it? Because this current is flow into the node from this side and it's leaving from this. So if we stick into this passive sign convention, so the actual induced voltage according to the given sign convention is reversed. So then we can claim that, so this V out is actually can be applied. For example, if I want to evaluate the current gain, so AI, output current divided by the input current. So output current, actually I out can be treated as minus V naught V out divided by RL, because like according to the sign convention, the current should be flow into the node, but due to that current flow, the induced voltage across this RL would be simply minus of V out. So that's this minus is there due to the sign convention. So then minus V out over RL. So your input is actually Vi divided by Zi. So ultimately you can have this V out of Vi into Zi over Zi. So V out of Vi is actually, so this voltage gain. So then if you want to map your voltage gain to the current gain when you have this load resistance in the circuit. So this is the simple relationship. Your current gain is simply negative of this AV into ZI or ZA. So what's the real physical meaning of this minus sign? So this is a gain. Is it means that you are getting a negative gain, means you are getting a loss? No, this minus sign basically introduce a 180 phase shift. So this actually introduce a 180-degree phase shift. So this your current gain is minus of a certain value into voltage gain. So it doesn't mean that due to this minus sign, so you are having a voltage gain, and but due to this minus you cannot claim that your current gain is negative. So if it is in dB domain, you know that if this minus sign gives a kind of a loss. So this is not the case. This minus sign basically reflects the kind of a phase shift. So if you have -1, so it means that the whatever the voltage gain, so you are getting a kind of a signal, and for the voltage, so the whatever the current gain is simply reverse. So then, so we can see that what's the real impact of having this minus sign in this if we deal with this time domain quantities in the later slides. So what I want to highlight here is this minus sign. It doesn't mean that you are getting a negative gain. So this minus sign basically represents a kind of a 180 phase shift. So we'll go to one example, so then you can basically, yes, before moving to that, yes, now this is your transistor. So now I'm referring this common emitter configuration. So this is your emitter, this is your base and collector. So we know that between this base emitter junction, so we have a kind of a diode, forward bias diode. So we just replace this forward bias diode between this so with the base emitter junction, and at the same time you know that so this collector current is simply driven by the base current. So this collector current is simply driven by the base current through this beta times this current. So you can just replace this collector base junction also through a kind of a current source. So beta times IB. So the value of the current source would be beta times IB. So then we basically implement the relationship between base current and the collector current through this current source, current control current source, CCCS. So then this you know that base emitter junction should be forward bias, so we can simply replace the base emitter junction with a kind of a simple diode. Okay, so then, so what would be this diode actually? So now we are dealing with AC quantities. So let's think of like, so you have a diode, so this diode characteristic is something like that. So this is the base emitter junction voltage and this is the current. For this case it's I. So then, so if we want to replace, like for example, now we have a diode, so now we want to replace this diode with a kind of an impedance. So we need to replace this diode with a kind of a impedance. So how do you remove this diode with the corresponding impedance? So then it should be like, so this impedance would be, so just measure the voltage, and if we just divide it with the current flow through that diode, so it gives a kind of an impedance. But the problem is this diode characteristic is not a linear one. So it basically follows this kind of a Shockley type of equation. So it's aligned with the Shockley type of equation. It's not a linear one. So then depending on the operating point, so if let's assume if the dart is operating here, so if it is operate here, so this is the resistance or the gradient. So if you operate the dart here, this is your gradient. So if it is here, it's this the gradient. So likewise, depending on the operating point of the diode, so the resistance value itself given to the input will be simply varying. So that's why we call it as a dynamic resistance. So this is a kind of a dynamic emitter resistance. So how do you get the dynamic emitter resistance is this. 26 millivolt divided by IE. So this is actually DC emitter current. So keep in mind, this is not the AC current. So this is actually the DC emitter current. So then to evaluate this dynamic emitter resistance, you need the current flow through the emitter when it is in DC mode. So then without having this DC analysis completed here, so you cannot find IE. This IE itself is a kind of a DC emitter current. So to obtain this DC emitter current, first you have to analyze the transistor circuit in DC domain and find out what would be the emitter current. So then you can plug it to this equation 26 milliwatt divided by IE. So it gives the value of RE. To get the RE, you need the DC emitter current. So to get the DC emitter current, first you have to analyze the circuit in DC domain. Yes, now we replace this emitter diode through a kind of impedance, which is now for a transistor is denoted by this dynamic emitter resistance Re. So we can basically get this dynamic resistance value by dividing 26 millivolt by DC emitter current. So let's stick on this one. So if you want to evaluate the dynamic emitter resistance, just plug this equation and find out the DC emitter current by doing this DC analysis for the transistor, and then plug it to here and get the value of the dynamic emitter resistance. So most of the case RE will be given, so then you don't need to worry about this RE. If it is not, so you have to do it in DC domain first and get the IE and just plug it to this one and find out RE. So without RE you cannot move forward for this AC analysis part, so you need RE. So then now I replace this diode with this emitter resistance RE. So now we have this base and emitter, we have a input impedance of like RE, we have current source and so on. So now what we can do is now this is a kind of a combined model. So we have input and output. What we can do is, so we can further simplify is to separate your input circuit and output circuit, because if you basically separate your input and output circuit, so then it's easy to analyze it. With if those inputs and output circuits are simply connected to each other, so then the evaluating this in branch currents and voltages may be too complicated. So we can see one example, but if we basically isolate your input from the output, so you can simply treat your input separately, and so you can treat the output independently. So what we simply do is we simply isolate the input and output and come up to a kind of a very simple model. So how do you remove this or how do we simply isolate this input and output? So we can replace this input using an input impedance. So what about the input impedance for this case? So now So we have a voltage drop across this RE, which is equal to IE. So IE is actually the sum of these two. So we have a total current of IB plus beta IB. So the current flow through this current source plus the base current would be the total current, which is basically flow through the RE. So we have a resistor. So we have a resistor RE, and the current flow through this one is like 1 plus beta times IB. Okay, so here the voltage is VI, current is I. So if you want to decompose this, or if you want to simply isolate this input from the rest of the circuit, so we can do like that. So we have kind of input impedance, and we have, so then what would be the input impedance induced due to this RE, or the emitter resistance? So how do you get? So the total voltage appear across this resistor would be current times the resistance. RE is the volt resistance, and the total current is 1 plus beta times IB. So this is actually the voltage across this RE. So what's the current flow through this network? If it is an input circuit, so it's like IB. So if you just replace this one, so then this is the input impedance, RE. So we can approximate into beta times RE. So that's why we have this beta RE there in the input side. So we'll simply isolate the input from the output by replacing this emitter resistance through a kind of an input impedance. Now the input impedance would be beta times RE. So it means like due to this emitter resistance induced by this diode, so it basically influenced to the input circuit as a beta times of that. Whether you add a kind of a small RE resistance to the circuit, so it influenced to the input circuit with a kind of a beta time. So this was basically found in this biasing methods also. If you have an emitter resistance in the biasing circuit, so the influence to the input circuit, once you apply this Kirchhoff voltage law, you can see that RE, capital RE, simply multiply with 1 plus beta. So it means whether you put a kind of a small resistance to the emitter, so the real impact to the input is beta times RE. Similarly, so once you isolate your input from the output side, you can simply replace the impact of this RE at the input circuit with the beta times RE resistance, not the simple RE. So the simple RE is the emitter resistance. Once you simply decouple your input and output, the influence of RE reflects to the input circuit. It's not just RE, it's just beta times RE. So that's why we have this beta times RE in the input resistance. So then you can simply take the output circuit out. So we have the output between this collector and emitter, so we can simply replace this with the current source. So then this would be the simple RE model. So you have a input resistance of beta RE, and output you have a current control current source of beta IB. So this is the very simple RE model for a transistor BJT. So then you can, so previously we discussed about how we can get the AC equivalent circuit. So then we can simply replace the DC AC circuit with this transistor model. So you can just remove the transistor here in the circuit, because once so during this previous discussion we get that AC equivalent by keeping this transistor model as it is. So we just apply the uh, conditions and simplify the rest of the circuit by keeping the transistor as it is. Now what we can do is we can replace this transistor with this RE model. So with this RE model, so nothing else. So you just remove that this transistor symbol from base collector emitter junctions and plug this model to there. So then we don't have any transistor anymore. So we have a kind of a beta re resistor and a kind of a beta IB current source. So then you can simply analyze the circuit by keeping this resistance and current sources in the circuit. So we'll see a very simple example. So then you can have a kind of a idea. Okay, now think of so this we'll start with this common emitter fixed bias scenario. So common emitter configuration where your emitter terminal is common for both input and output side. So we use this very simple biasing technique called fixed bias. So then fixed bias, we know that. So we have base resistance simply connected to the source. So we just take a portion of this supply voltage and apply to the base through this whatever the RB. So this is the circuit. So this is the circuit. So see that. So it is basically mixed with all AC and DC components. So we have a supply voltage RC resistance. So there won't be any resistance to the emitter. So we have RB base emitter collector junction, and your load would be basically coupled to the C2, and your input is basically coupled to the C1. So you don't have any input impedance, or sorry, the internal resistance for the source. So we have VI as a AC input and II as a AC current. ZI is the AC input impedance, Z out AC output impedance, V out again output voltage in AC domain, I out also is. So the rest of the parameters are kind of DC quantity. So how do you convert this full circuit configuration into AC? So you can replace this capacitor with short circuit elements, and the supply voltage is set to 0. So once you set to 0, so it basically becomes a ground term. So this becomes a ground term. So then once you draw this one, so you have this transistor, and this is simply short circuit. So this collector is simply this RC is simply connected between collector and the ground. So this is collector and the ground. So once you come to the input circuit, you have base resistor, which is basically connected in between base and the ground. So the base and the ground. So emitter is just short circuit through the ground. So then, so we can just plug this currents and voltages as it is. So now we basically replace this transistor symbol using this whatever the model we stick into. For this case, we use this RE model. So we know that how we, so this RE model, we have this input resistance or the impedance and a current source. So we can simply connect this base emitter junction through beta RE resistor. So see, so this beta RE resistor, and this collector emitter junctions through the current control current source. So this is current control current source. So in addition to that, so just ignore this R out for the time being. So we have RC. So we have this beta IB coming from this RE model, beta RE coming from this RE model, and RB is the real base resistance. So now we have this kind of arrangement. So this is RC, this is beta IB, this is beta RE, this is RB. So this is plus minus V in. So this is your input current, this is your output current, so this is the output voltage. Okay, so these are output and input currents. So this is your transistor, this is the transistor, and these are the, this is your base, this is your emitter, this is your collector. Something else. So then so you can basically evaluate the voltage gain for this transistor, current gains, then input and output impedance. So we'll start with the input impedance. So input impedance is actually the resistance you can see from this end. So this is your input impedance, is a die. So if you see the, if you see from this end what's the total resistance induced by this input circuit, so you can see RB and beta RE which are in parallel. So then the input impedance means the combination of these two, parallel combination of parallel combination. So this is parallel combination. So the parallel combination of RB and beta RE. So you can just plug equation where you can get the parallel combination of two resistors. So then substitute it here, so you can get the input impedance. So input impedance is just the parallel combination of RB and beta RE. Similarly, what happens to the output impedance? So output impedance actually, if you see from this end, what is the resistance or impedance you can see from the output circuit when your input is 0. So if you make your input 0, what you can do is you can just short circuit this one. So then what about IB? So IB simply 0 because no current flow through the input circuit because your source is simply set it to 0. So this is short. So the input current is 0, then so whatever the base current flow through this branch is 0. So then what about the value of this current source? Beta IB, which is again 0. So if you have this 0 value for the current source, it means, so this is actually open, isn't it? So this is open simply. So then what's the impedance you can see it from this end? So it's is simply RC. So no any other resistors. So the impact of this current source is simply vanished due to this because we set the input to 0, so then this current source is simply vanished. So if you have a current source, you cannot simply evaluate the input impedance like that. So you have to evaluate these currents and take the ratio between V out and I out. So it's a bit tricky, but from the definition itself, so you can simply take this output impedance as a ratio of voltage and current when your input is 0. So once you set the input 0, so it's like just short circuiting your input. So then the current source appearing in the output circuit is simply vanished. So you can simply calculate the output impedance as RC. So then what about the output voltage? So V out. So you have current source here now. So what about the voltage at V out? So this V out is like, so this is the current, I out is simply, so if this is open, so there won't be any current flow from this node. So current flow from this is 0 because this is open. So but there is a current generated by this current, so it's just flow through this RC only because no current flow from this output side. So I out is basically 0, and there's a current flow through this RC, which is basically generated by this beta IB current source. So then the direction of the current flow is actually from here. So then this would be plus and this would be minus. So this is plus and this is minus. So if we stick into the sign convention, V out would be minus, because the induced voltage is to the reverse direction, RC times current beta IB. So this is the induced output voltage according to the sign convention, minus RC or the Z out times IB into beta. So what about the input voltage? So this is your IB, this is your II. So the input voltage is just a voltage drop across this one, IB times beta RA. IB times beta RA. So then what about the voltage gain? AV, V out over V in, which is equals to minus RC. Beta IB it simply cancels out and is, so this is the gain. So this minus basically gives a kind of a negative phase shift or kind of 180 phase shift with respect to the input signal. So this, as I highlighted previously, this minus sign basically represent the 100 phase shift between the input and output waveform. So if you just take these two channels out from this input and output and plug it to the oscilloscope, so your input signal is something like that and your output would be something like that. So it's having this 100 phase 5-degree phase shift. So this is your output and this is your input. So due to that 180-degree phase shift, so you will get the negative sign for the voltage gain. So this negative sign is not a kind of a negative gain, it simply represents a kind of a 180-degree phase shift with respect to the input. So if you have a kind of a input signal which is indicated in black line, so you will get a kind of an amplified version simply inverted by 180 degrees. So this is the physical meaning of this negative sign. So then the voltage gain is simply controlled by this RE, simple RE and the capital RC. So then if you want to design a kind of an amplifier with a certain gain, keep in mind this is one of the controlling parameter. So if you change the collector resistor, so it simply impact to, it affects to the voltage gain of the entire circuit. So if you really like it, so if you want to increase your gain of the transistor, think of changing your RC properly. So once you change your RC, you can boost your gain. So from this analysis, you can get two conclusions. One is like, so your output signal is simply introducing a 180 phase shift with respect to the input signal, and at the same time the gain is a function of RC. So then once you change your collector resistor, so it's basically affects to the gain of the entire amplifier. So next move to the next circuit. Yes. So this is like collector feedback bias. So we know that. So in the collector feedback bias, so we have this RF resistance basically between this collector and base. So the rest of the configuration is very similar. So we have this. So once you convert into AC equivalent circuit, So you can simply replace this with short circuit. This is again short. This is simply grounded or set it to 0. So then we can simply put the transistor like that. So emitter is simply grounded, and this collector is basically connect to the ground through RC. So this is RC, and this is your V out. So this is your I out. And from the input side, so we have what happens to the circuit. So we have a RF resistor in between base and the collector. So this is your collector. So this is your base. So then we have this RF here. This is the input current, I in, this is the input voltage. So this is the circuit. So once you replace this transistor with this RE model, so what we can simply do here, so you will ended up with this kind of so this is the input impedance, this is the current source which is basically in the output circuit. So then whether we replace the transistor with a kind of RE model which has this simple isolation between input and output with this feedback resistor, so it again create a kind of a correlation. So this is the RF in the feedback cycle. So then we have, this is a bit tricky to analyze because this due to this RF, so you basically build another correlation between input and output. So then you have to deal with different approaches to solve this one. So you can go through this one, see how we can evaluate the voltage gains and so on. So this is a bit tricky case because due to this RF, whether you separate your input and output from the transistor model itself due to this feedback resistance, so it again introduces a linkage between input and output. So you have to carefully analyze those currents, and then accordingly you can find the voltage gains and input impedance as well. Yes. So then we'll discuss one more. So this is voltage divider bias. So how do you map it to the AC equivalent circuit? So let's think of. So how do you convert it to AC equivalent circuit? Set this to 0. So then this become grounded, and this is short, this is short, and this is short. So due to this replacement, so then there won't be any impact from RE to the circuit. So let's draw this transistor circuit. So this is your emitter, this is your base, this is your collector. So then, so you have a RC in between collector and ground. So this is your RC. So this is plus and minus, this is V out, this is I out. So this is IB. And what about input? You have two parallel resistance, R1, R2, R1, R2. This is VI. So this is beta RE, this is beta IB, this is your IC, and so on. So then how do you get this input impedance? So the input impedance is the impedance, you can see it from here, is it I. So once you look into the circuit from the input side, you can see three resistors are in parallel. So then the input resistance would be R1 parallel, R2 parallel, beta RE. So this is the total input impedance, you can see it from the input side. So the parallel combination of R1, R2 and beta RE. Similarly, so you can evaluate the output impedance. Is it out? So once you set the V out, V into 0, it means like, so once you set the V into 0, so then this is short, so you don't see any base current, IB equals 0. So then this is no longer be there, so it's open there. So then RC, output impedance is simply RC. So then you can evaluate the voltage gain. So you know that, so the output voltage V out is simply minus RC times beta IB. So what about your input voltage IB into beta RE? IB into beta RE. So then this is equals to minus RC over RE. Very similar to the very first case. So then there won't be any impact on this transistor configuration to the gain, but so you can do some stable biasing through this voltage divide. So the gain from this very first very simple fixed bias method and this voltage divider bias method is very similar. It's minus RCORE. But like once you think of biasing a circuit and make it very stable, so then the voltage divider bias is the best uh, compared to the fixed bias method. But fixed bias is very simple, but this is where voltage divider bias is more reliable and it's adaptive. So but the gain wise both are same. So the collector resistor is the one affecting to the gain of the transistor circuit. So then we'll see one more. So here we have an emitter resistance. So the simple difference here is we have emitter resistance, but we don't have any emitter bypass capacitor. So if you put a capacitor here, you can simply remove the impact of the emitter resistance. RE, if you place this CE here, so you can just remove this impact of RE. But if you basically ignore this bypass capacitor, so you have this RE in the circuit. So then this is your transistor model. So then this base is collector is simply connected to the ground through RC. This is your collector, it's connected to the ground RC, and this is your emitter, so it's connected to the ground through RE. It's connected to the ground through RE. So we have RE there now in the circuit. So then base and ground, there's RB, base here, now ground here. So this is your RB resistance. So if you mark this input and output voltages, so see what would be the input impedance. So if you see the resistance from this end, so you can see, so you have a resistance here beta RE, and you have another resistor here. So it's equals to the total current flow through this resistor is here beta IB. So here IB, so the total current is 1 plus beta IB into this resistance R. And the total current would be total voltage across this is like IB into total voltage from here. So it's like IB into beta RE plus IB into 1 plus beta, the total current flow through the emitter resistance into RE. So if this is the entire drop across this. So if you divide by the input current IB, so it's gives the input impedance. So then the input impedance is beta RE plus 1 plus beta RE. So see, like all the time this emitter resistance would appear in the input side as a with this beta factor. So if once you approximate it, you can have this beta times RE, but this is the actual value, beta times simple RE plus 1 plus beta times capital RE. So for the output side, what happens? So if you set your input to 0, so this is short circuit, so then there won't be any base current. So then this current source is simply 0, so then this becomes open circuit. So then once you see it from the output side, Z out would be just RC. So there won't be any impact from RE because this is simply open. When you set your input to 0 volt, so then base current is 0, so then there won't be any current source here. So once you evaluate the output impedance or the impedance from this output side, so that RE simply vanishes off because this is open circuit, so the only RC is appearing at the output, so the output impedance is simply RC. Okay. Okay, next is like a, so for example, now for this analysis we basically did without this input resistance or the input impedance of the source and the load. So if you have loads and the input resistance, see like what happens to the circuit. So if you have load in the circuit, which is basically connected to this capacitor C2 and RL. So this is short means like, so this RL is simply coming to the AC equivalent model, and it's appear between the collector and the ground. So this, see, so this is your collector, this is your ground. So this RL is simply appear across this collector and ground. So if you have internal resistance for the source, so it's basically appear as a series resistance to the rest of the circuit. So this is the, now this becomes the circuit. So until then, so we basically analyze the circuit having this block. Okay. So we have R1 and R2 parallel, beta RE current source, and so we'll just omit this one, RC. So with this internal resistance of the source and the load, so we have additional components coming to the picture. So then if you basically want to evaluate the effective load, see, like, so there's a combination of RC and RL. So if you want to evaluate the entire voltage gains between V out and Vs, so you can think of connecting this RS and RL also into the picture. For example, if you want to evaluate the output impedance, so you know that we can set the input so to the 0, so then this becomes 0, so then you can't see this IBRB current source in the output side, so you can simply say that the output impedance is parallel combination of RC and RL. Okay, so then so if you want to evaluate the output voltage, so V out, which is actually equals to, so you have this parallel impedance, which is now Z out, So you can simply say that this B minus beta times IB into this Z out. So which gives the output impedance. So what about input voltage? So this is the output voltage. So what about the input voltage? So you have base current flow through IBRB. So the input voltage is beta times RE times IB. So then this is beta to beta and I beta. So then it becomes voltage gain is actually minus Z out over RE. Z out is actually the parallel combination of this RC and RL. So in the previous case, your voltage gain is simply RC divided by RE, which is actually called the no load voltage gain. No load voltage gain. So then for these cases, you don't have RL. So once you connect the load to the circuit, so it's kind of a, so it's like loaded voltage. So for this case, you have kind of a circuit loaded by this RL, and you can evaluate the actual voltage gain appear across this RL, which is again a function of RC, RL, and simple RE. Similarly, you can find the voltage gain between the input and output. So up to now, without this external resistors, so we basically evaluate V out over V in. Now we can evaluate V out over Vs, which is simply the Vs is the input source. So then it's like end-to-end voltage gain. End-to-end voltage gain can be simply derived from this circuit. So then you have to treat this one. So here, like for example, so this is a parallel combination of R1, R2, and beta R. So once you evaluate it, so your input side is something like that. So you have input side, you have a series resistor RS. So you have here, so you have this is Vs, this is RS. This is actually parallel combination of R1, R2, and beta R. So then you can simply take expression for this Vs, and similarly you can map this output. So this is very simple. So this is isolated from your input, so you can treat your output separately, so and get an equation for V out, and simply combine these two equations. One is basically took it by applying this or considering your input circuit, and then the second one is basically you take it from this output circuit. You can just combine it and get the end-to-end voltage gain for this kind of a circuit, where you have this load resistor and an internal resistance for the source. So keep in mind there may be two gains you can easily value. One is this no load voltage gain. So for this case, so your load is simply zero. So you don't have any load connect to the output. So it's just open. So again, you can evaluate a voltage gain with a load. So it's like loaded voltage gain, or just see like voltage gain due to this RL is simply a function of RL and RC. So keep in mind, like, so then if you basically, if you do not match your impedances properly, so think of your gain is simply reduced, because you know that for this kind of a scenario, your gain is a function of RL, RC, and simple RE. So in the previous case, once we refer this no load voltage gain, so we have voltage gains as a function of RC and simple RE. But with the addition of this external load RL, so it basically a function of load resistance as well. Once you introduce the input resistance to the source, so it's also coming to the picture as well. So this is the simple briefing about this AC equivalent circuit. So for the exam, you will basically get a very simple transistor configuration. So you should be able to draw the AC equivalent circuit and evaluate the corresponding parameters. Most probably you will be able to evaluate the input and output impedances, voltage gain, and just to discuss what would be the output. And so because for most of the cases you will getting this minus sign in front of this gain, so you should be able to draw the input and output variation. So keep in mind, once you have draw the input and output, so those are not in phase due to this minus sign. So whatever the output you are getting is simply uh, introduce a kind of a 180-degree phase with the input. So you can't just draw this is your input. So you can just draw this is your input and this is your output. So you should be clear on that. So due to this minus sign, your output would be simply inverted. Okay. So otherwise, so you will get a kind of a wrong message. So this is actually what I want to highlight during this session. So if I give a kind of a transistor circuit, so ideally you can do the DC analysis and do the biasing and select the currents, voltages and resistors accordingly based on the given values. So either you may get this current and voltages and ask to evaluate the resistance, or else you may get this resistance values and ask you to evaluate the operating point parameters. So then if you are given a kind of external AC input, so you can simply analyze the circuit in AC domain. So then the same circuit can be simplified to AC equivalent model by replacing capacitors with short circuit and inductors with open circuit element, and the source can be simply the impact or the effect of the source can be simply ignored by letting the source voltage to zero. So then you can have a ground introducing in there in the source. In addition, instead of the source you have ground terminal. So then with that you can basically fold the circuit. So whatever the resistors are basically connected to the supply voltage is simply folded and connected to the ground. So it's just a kind of a folded arrangement. So then think of like simplifying the circuit by considering this folded arrangement due to this ground appearing in the supply. So then you can simplify the circuit and evaluate the input impedances, output impedances, voltage and current gains with or without these loads and internal resistance. So this is the whole discussion about this AC analysis. So I believe like you can have kind of a brief idea. So if you have any questions, just drop me email so we can discuss through email, or if you really need, we can set up a kind of a discussion class during next couple of days. Thank you.